top-down network design. It's a Cisco Press text. Chapter 1, Analyzing Business Goals and Constraints. The normal question is, why bother analyzing business goals and constraints when we're talking about network design? And one of the big questions is, network design should be a complete process that matches the business needs to available technologies to deliver a system that will maximize the organization's success. Essentially, the network has to match, or the technologies of the network have to match the business. If it doesn't, then the business isn't maximizing its success. In the LAN area, it's more than just buying a few devices. In the WAN area, it's more than just a phone company. These are specific design requirements for a specific organization to maximize that organization's success. So let's start at the top. Don't just start connecting the dots. You have to look at the business and technical goals first and understand them. Understand the business goals and objectives for today, tomorrow, and next year. Explore divisional and group structures to find out the network servers, services, and where they reside. Determine what applications have to run. What network components for each application. What are their requirements? Focus on layer 7 and above first. Meaning, let's focus on the application and end user. Remember our 7-layer of our OSI model: application, presentation, session, transport, network, data link, and the physical. Those are our 7 layers. So the structure design, a focus is placed on understanding the data flow, the type, and processes that will access or change. Here we're focusing on the data itself. We have to understand how it's going to flow from end to end, from server to client, from client to end user. The client or the end users could be internal, could be external. Who's going to be using it? What's going to be the data flow? What data types are going to be? What type of processes might manipulate that data? Does it have to be secure? Does it have to go between locations, geographical locations, or continents? All those other things that you have to understand before we can start designing. Another focus is placed on understanding the location and the needs of the user and the user communities that will access that data, will use that data, and will process that data. Several techniques and models can be used to characterize that. One of the big ones is new user requirements and structure for future system design. It's a logical model. It's developed before any physical model is selected. The logical model will represent the basic building blocks that will divide the network into functional, logical groups and will underline the overstructure of the system. The physical model represents the devices and specific technologies and implementation. So how do we design these? So if you've ever done software, you should be pretty familiar with the System Development Lifecycle, or SDLC. Doesn't mean synchronous data link control or system development lifecycle. It really just depends on the course. This is a fairly common acronym, so keep that in mind. The typical systems are developed and continue to exist over a period of time, and that's that life cycle. So is there a graphical representation that we can look at? Here we go. We develop logical design. It kind of depends on what layer we're working with. We analyze requirements, develop logical design, develop physical design, test, optimize, document design, implement, test network, monitor and optimize performance, and start over. Over and over and over. Phase 1. They analyze the requirements. It will analyze business goals and constraints, objectives, both short-term and long-term. It will look at technical objectives, technical goals, and trade-offs of such technology. It will characterize the existing network, what components are good, what components are bad, how it's laid out both logically and physically, and it'll help to characterize network traffic. Phase 2, the logical network design, that will be the network topology design at the logical view. It will design models for the addressing and naming of devices. This will start selecting the switching and routing protocols, what type of STP might be used on the switches, what type of routing protocols might be used on routers. Is it going to be EIGRP? Is it going to be RIP, OSPF, BGP? What? If we're doing multiple site locations, are we doing frame relay? Are we doing MPLS? What layer 2 technologies are we going to be implementing so that we can have interconnectivity between remote locations? That's things that are thought about and done here. We're also going to start looking at a network security strategy as well as management strategies for that network. Security should be pretty much built into every layer. It's sadly not, but here is where we start having to really dive into our security strategies as we start designing our logical flow. Phase 3, the physical network design. This is where we're going to be selecting the technologies and devices for our network. If we're using MPLS, if we're using frame relay, this is what's going to be decided here. Then what devices are we going to use? Are we going to use all Cisco devices? Use a mix of Cisco and Juniper and Sonic walls? Here's where you have to decide what type of devices are we going to be using. This would also be selecting devices for our design. So it's not always about our campus network. It could be for an enterprise network. Big thing here is we're selecting our technologies and devices for our network, regardless of the type of network. Phase 4, the testing phase. This will test, optimize, and document the design. We'll test it, we'll optimize it, we'll document, and we'll repeat. We'll test, optimize, and document until we have the desired optimization. So, there's always this fun one. This is our PDIOO network lifecycle. That is plan, design, implement, operate, optimize, retire, or repeat. Plan, design, implement, operate, optimize, retire, or again, repeat. So next, business goals. Why do we care about business goals? Because the business is there to make business. Normally the business goals are going to be increase revenue, decrease costs, reduce operational costs, improve communication, maybe shorten life cycles, expand their markets, build partnerships, offer better services. So how can we take this and apply it to technical goals? That's the big thing. You have to remember the business wants to decrease costs and increase the money it's making. So trying to do network designs that are going to be too expensive while not really increasing revenue probably won't go very far. Other business priorities could be mobility, security, resilience or fault tolerance. Could be disaster recovery or business continuity after a disaster. What projects are going to be prioritized? Are there any things that are going to require QoS or COS? Are there low latency requirements for applications? Things like voice. So resilience means how much a stress a network can handle and how quickly the network can rebound from that problem. That could include security breaches, nature and natural disasters, could be error or catastrophic software or hardware failures. It's believed that some experts have a mild dislike for the word resilience, as it sounds too much like a stretched rubber band. So depending on the book that you're reading, it might be called fault tolerance, not resilience. So business constraints, budgeting, staffing, schedule, politics, and policies. How could they affect our network design? It's all about growth and scheduling. If we don't have the time to implement the technology, Because of schedule conflicts, that won't work. It could be political. Politics are always a big one. Could be staffing or expertise. Could be budgeting. They could just not be able to afford the current design. So these are all constraints that have to be considered when designing a plan. So first thing we have to do is do some basic data collection. Before our first meeting, we need to understand the client. Are they internal or are they external? We should also collect some basic business related information, like what do they do? What do they produce? What services are supplied? What are their financial viability? What are their customers? What are their competitions? Do they have any advantages or disadvantages? These are all things that you might want to be able to know off the top of your head before going into a new client trying to design a new network. That way you can tailor that network design to that business goals. So when you meet with the customer, you want to get a concise statement of the goal of the project. What are you trying to solve, or what solution are you trying to push on them? How will the new technology help them? How will it be more successful? And how will that help their business be more successful? Lastly, what has to happen for those projects to succeed? That's a big one. What will happen if the project fails? Are there any consequences to that? What are the mission critical or the critical business functions that must be there? If this project fails, will it affect those mission critical processes or functions? Is the project viable and visible to upper management? Are they on board with it? Who is supporting your design? Is management? Is it just end users? You also need to look and discover any type of biases. Some companies will not use Juniper equipment because one of their managers hates Juniper. So you need to understand the biases. You also should understand, do they avoid any specific types of technology? Some companies refuse to use BYOD. The idea of bringing user devices into the network is absurd to them. So you have to be able to understand the technologies that they're willing to use and not willing to use. Does the data people look down on voice to people or vice versa? One of the big things here is, can we understand the data? Are we going to be able to support the data and all of their needs? You also want to talk to their technical and managerial staff as well as end users. You want to make sure that you're understanding the full scope of the network design. Once all of this is ready to go, make sure to get an organizational chart. That way you have a general structure, who reports to who. But what about security? That's always a big one. Before meeting with the customer or during meeting with the customer, get a copy of their security policy. How is it designed? How is it going to have to be redesigned to support the current new design that you're going to be proposing? Will there be new designs that will affect the policy? How are you going to make those changes? Are you going to make those changes? All questions to bring up. Is the policy so strict that you, the designer, won't be able to do your job? That's always a good question. Start looking over and categorizing network assets and the security that it should be protected, and to what degree that security must be there. Look at things like hardware, software applications. You may have to look at intellectual property, trade secrets. How are those being protected? How are you going to keep protecting them? Those are all big things to look at and review. Understand the scope of the design project. Is it a small scope? Is it a big scope? Can you break the larger scopes into smaller several scopes or milestones so that you can complete them? Use the OSI model to clarify the scopes. Use the scopes to help fit the budget and capacity. and the scheduling. That way you will be able to successfully complete the project. Gather more detailed information as required. Things like user communities, data stores, the protocols, the current architecture and performance, that should all be discussed. You should be looking at other business needs like applications. One of the first things within the research should be applications and how they're going to be impacted. Things like data stores, those are all really important things that you are going to have to know. So can we have some type of general chart for us to use? Sure. Here is a network applications general chart so that you can do the name of the application, the type of the application. Is it a new application? What is its level of credibility? Is it mission critical? Does it have to be the first item backup, second item backup? And it gives you room for comments. This should be done for all applications in a network. That way, if an application ever fails, you have a way to go in and manage it, recover it, and again, you kind of know what thing has to go first. So in conclusion for this is all a systematic approach. Focus first on the business requirements, goals, and objectives, looking at the constraints and applications, understand the customer and the customer's corporate structure, understand their needs, what are they wanting to do with it, also gain an understanding of the customer's business style. So last slide before we finish, some general thought questions. What are the main phases of network design per the top-down network design? What 6 items are there? What are the main phases of the network design per the PDIOO approach? Is that going to be repeat or retire? Why is it important to understand your customer's business style? Why is it important to understand your business goals, objectives, long-term wants? And what are some of the goals for the organization today? How might they differ from tomorrow? So that's actually it for chapter 1. It's a nice start of understanding business goals. So I wanted to thank you, and I will see you next time. Top-down network design from Cisco Press, chapter 6, designing models for addressing and naming. So this chapter mainly focuses on IP version 4 addressing and DNS naming conventions. So, without further ado, some of the guidelines for addressing and naming. We use a structured model for addressing and naming. It's pretty straightforward. The address and name have a hierarchy design. Decide in advance if you'll use some type of centralized or distributed authority for addressing and naming. Pretty much, are we going to be working with public or private addresses? And are we working with dynamic or static addressing and naming schemes? Realistically, most companies will probably be dealing with a handful of public addresses and a lot more private addresses. My day job, I work as an instructor for a large college. Realistically, we're using probably 4 or 5 public addresses, and we're using almost 10,000 private addresses. And then our private addresses map dynamically certain ones to our public address. A few map dynamically to our public address. Our voice over IP system is a static NAT from our internal private address for our VoIP server to the public address that it receives calls on. So it's not always a one or the other, it's a combination and how you combine those combinations. So advantages of using a structured model is it makes it easier to, one, understand how your network is mapped out. It helps with operating network management software with recognized devices and protocol analyzers like Wireshark. It also helps to meet goals for usability. Also helps design filtering or access control list filtering on firewalls and routers. and it's a little bit better way to do route summarization. So I'm going to assume that you already know what a few of these things are, like ACLs, what NAT is, what summarization is. If you haven't, go ahead and look those videos up because I know I'll be doing videos for those here shortly. And those are key things that you need to understand when you start working with addresses. So our slides today is going to assume that you don't really know a whole lot about addressing. So we're going to start off very basic and we're going to get into basic subnetting. So first of all, public IP addresses, how are they managed? In the US, they're managed by the group name of Internet Assigned Number Authority, IANA. Users are assigned an IP address, normally by the IP provider. Unless you're paying for a static address, home users normally only receive a dynamic address. That means it's an address that may change. Not that it does change, but it may change. The ISPs get their allocation of addresses from their appropriate regional internet registrar. It's a tiered system. So your provider gets its internet from a provider above it. And they again work out the appropriate addresses that your provider is allowed to hand out. So most end users will connect to a tier 3 provider. Our tier 3s will go up to a tier 2. And normally there's a few tier 2 providers and they will support several tier 3 providers. 4 or 5 tier 3 providers will probably connect to one tier 2. And then those tier 2s will combine 2 or 3 of them into a tier 1. Within the US, Verizon communicates with a huge tier 1 provider, and they provide internet for a lot of companies because they provide connections to the internet to I want to say 10 to 15 tier 2 ISPs, and then those tier 2 providers provide it to sub-providers, to tier 3 providers. So if you think of like a root system, that's what this design is. Is IANA the only assigned numbering authority? No, it is not. So it all depends on the area that you're in, because here are some of the regional internet registries. In America, it is the ARIN. If you are in the Middle East or Europe, it could be RIPE. If you're in the Asian Pacific Network, it could be the APNIC. In Latin America, it's the LACNIC. If you're in Africa, it's the AFRINIC. It just kind of depends on your area. These are the regional groups that hand out addresses to their respective countries and all of the address information that they are allowed to use. So those are how we get public addresses. But what are some private addresses? Private addresses, assuming we're using a class full network, is any address that starts or is between 10.0.0.0 through 10.20 or 255.255.255. That's a class A network, and anything in that 10 range is set aside for private use. In the class B range, anything in 172.16.0.0 through 172.31.255.255, those are all private addresses set aside in the class B range. In the class C range, that's 192.168.0.0 through 192.168.255.255. So, meaning an address 172.32.0.0, that's not a private address. That's outside this range. So, they're not classified or set aside as private addresses. These are the only current IPv4 private addresses in existence. So criteria for using static versus dynamic addressing. Essentially, how many computers do you have? What happens, or what's the likelihood that you may have to renumber or rename some of these? What about, do you have any need for high availability or security concerns? Do you have enough staff to tackle the importance of tracking the IP addresses? What happens if the end users need more than just what you provide them for information? Do you have enough people that go manually configure them again? So realistically, what I do is static resources that normally do not change. Printers, servers, routers, switches, management devices, IP cameras. Those are all good things that probably should have a static address. Things like end users probably should have a dynamic address just for easeability. So how many parts are there to an IP address? There are two major parts. There's the prefix, or the network portion, and then there is the host bits. Remember that an IPv4 address is 32 bits long. It is broken up into 4 groups, 4 octets that are 8 bits each. That's why the 255 in converting binary to decimal, there can only be 8 bits, and if there's 8 ones, that equals 255. If you're not sure how to do the binary math, check back one of my other videos, because I know I've done a binary video. Here we predefine the network length, and what that says is how many networks we can have and how many hosts per network, because we can manipulate this so that the hosts could be 200 hosts or 62 hosts or 5 hosts. We can do some manipulation so that our network can either grow or shrink depending on our prefix. An IP address is accompanied by an indicator of the prefix length. This is normally known as a subnet, and it's sometimes written in dotted decimal form, which is 255.255.255.0, or in slash notation, /24 for example. 255, again, is 8 bits. So we have 8 bits in the first octet, plus 8 bits in the second octet, plus 8 bits in the third octet, and 0 bits in the fourth octet. That is 24 bits. So in reality, that /24 is just letting you know how many ones or how many bits are in that dotted decimal. Then you do the appropriate conversion, and you can figure out either the dotted decimal form or the slash notation, just depending on which one you want to go with. Subnets, just like IP addresses, are 32 bits long. They specify which part of the address is belonging to the network and which ones are going to connect to the hosts. Again, it's either dotted decimal or slash notation for IPv4. So here it is broken up to you in binary. Again, notice 8 bits, space, 8 bits, space, 8 bits, space, 8 zeros. How many ones are there? There are 24 ones. So in slash notation, that'd be a /24. In dotted decimal, it'd be 255.255.255.0. What happens if we take this last one and we change it to 8 bits plus 8 bits plus 7 bits? That would be a /23. In dotted decimal form, 255 plus 255 plus 254. Guys, remember, this is the 1 position, 2 position, 4 position, 8 position, 16, 32, 64, 128, and you just kind of add up the positions. Again, you start with 1, and you just keep doubling. So let's look at another example. How many ones do we have? 8 plus 8, 16, 17, 18, 19, 20. So this is a /20. Dotted decimal, 255 plus 255 plus, we're not going to add a 1, we're not going to add a 2, we're not going to add a 4, we're not going to add an 8. So this is going to be 16 plus 32 plus 64 plus 128. If my math is correct in dotted decimal form, that should be 255 128.255.240. 128 plus 64 plus 32 plus 16. Let's look through one more example. Again, the slash notation, 8, 8, 17, 18, 19, 20, 21. So the slash notation would be 21. In dotted decimal form, here's 8 bits, here's 8 bits, so that's 255.255.128 plus 64 plus 32 plus 16 plus 8. We do not add the 4, we do not add the 2, we don't add the 1, so this should be 248. So 255.255.248.0. With this, it's practice, 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 practice. So let's do some designing for our subnetworks. So how do we determine network size? How do we figure out our computing subnet mask? And how do we figure out the computing IP addresses? So essentially, if we're looking at a group of addresses that contain all ones, we're talking in the host portion, that's a broadcast. If it's all zeros, it's going to be a network address. Network is a specialized address that we don't get to use. That's part of that summarization. Broadcast, same thing. It's part of those specialized area that we don't get to use. It'll be all ones. In the node portion for our hosts. If we're talking about the subnet portion, if the address is all ones, that's all the subnets. If it's all zeros, it's confusing. The addressing for IPv4 is not always the straightforwardest, so normally we're not really worried about the subnet portion. We're really worried about the node addressing, broadcasts, networks, versus usable addresses. Again, I'm going to be posting up subnetting videos here shortly. If you need a refresher on subnetting, check out those videos. So let's do some practice. We have a network which is 172.16.0.0. We want to divide the network into subnetworks. We don't know how many subnetworks, but we do want to recognize that we want 600 nodes per subnet. So the question is, what subnet mask would we use? What's the first address? What's the last address? Alright, so what I did was I already did a /24 here. 8 bits, 8 bits, 8 bits, all zeros. So how we do our subnetting, how many nodes? Same thing with our subnetting, except instead of resetting our binary conversion, we just keep going. So from the very far right, this is 1, 2, 4, 8, 16, 32, 64, 128. Normally we would restart and would go back to 1, we'd keep doing that. But because we're looking for how many hosts, we're not going to reset. So 128, 256, 512. This right here is going to give us 1024 hosts. So this is the one that we want. This one won't work because that only gives us 512 hosts. That one only gives us 256 hosts, so we change those to zeros. That's it. That's subnetting. So our subnet, again, as a slash notation, 8, and 8 would be 16, 17, 18, 19, 20, 21, 22. So a /22 would give us 600 nodes per subnet. Realistically, we're going to have a few hundred left over because we were at a toss-up between 512 and 1024. We need 600. So 512 is too small. 1024 is too big. But, I mean, would rather have more than not enough. So let's look at another example. Here we have 8 LANs or 8 groups, and they want to be their own subnets. So what subnet should we use? How many hosts per network do we have? Doesn't give us that information. So could we possibly one, two, three, four, oh, one more 0 there. So here's a /16. Could we break this up into 8 different LANs? Well, if we did 1, 2, 3, 4, 5, 6, 7, 8. This will only allow us to break it up into 2 groups, because that means we're going to have groups of 128. If we did that one, we'll have 4 groups, each group being 64. If we do this group right here, we could have 8 groups of 32. So what do I mean by groupings? That means, remember that range earlier within our private addressing? Those were ranges. 10.0.0.0 through 10.255.255.255. Those are ranges. And we can figure out those groups by the subnet and the last one. Here we have groups of 32. And that means our network will be, so the first network will be 0 through 31, 32 through 63, 64 through 95, 96 through 127, 128 through 159, through 160, through 191, 192, through 223, 224, 255. And those would be our 8 different subnets. So if we broke them up here in this octet right here, this third group, the addresses would be 172.16.0.0 through 172.31.255. And so forth. So 172.16.32.0 through 172.16.63.255, and so forth. Okay, so moving on, let's talk about IP classes. IP classes were considered obsolete because they predefined that subnetwork, and that doesn't really work. Sadly, you have to know them because most people in the industry still talk about them. And sometimes you may run into classful address schemes for businesses. I ran into them a few times. So you have to kind of know what they are. That's that Class A, Class B, Class C, and all how that works. So our next slide will give us a nice diagram for that. So Class A, if the first octet starts with any number between 1 and 127, it's Class A, and normally is used for very large networks. Class B is between 128 and 191. Again, that's in the first octet, first groupings, and that's for a large network. Class C, that's going to be anywhere between 192 and 223, and those are more smaller networks. Again, these are the predefined lengths here. So that's going to be a /8, /16, or a /24. With classful addressing, you couldn't modify them. You were stuck with those. So what that means is binary, so 2 to the power of 8 yields how many addresses? 16 million. Because we're going to take how many host bits there are. If there's 8 bits for the network, there has to be 22 bits for the hosts. -2, 1 for our broadcast, 1 for our network. And these are how many addresses that we could use for devices. Over 16 million for Class A. 65,000 plus for Class B. 254 for Class C. So let's talk about the waste of this. Class A uses 50% of the address space. Class B uses 25%. Class C uses 12.5%. And Class D and E, which are reserved, use another 12.5%. Very wasteful. So this led us to this design of what we call classless. And that is, we don't care about the class. If it's a 10 address, yeah, it's Class A, but we don't care. We want to be able to manipulate that prefix or that host boundary however we want, which is less wasteful. And it supports route summarization. Could also be known as aggregation, supernetting, classless routing, CIDR, CIDR, classless interdomain routing, or prefix routing. Normally it's just known as variable length subnetting, VLSM. So our supernetting, we move our prefix boundary to the left, not to the right. So our subnetting, we move towards the right. Here we have a /14. That means we're now working in the second octet. So let's look at our second octet, 16, 17, 18, and 19. We could summarize all 4 of these by looking at what they all have in common. We look at the second octet because that's where our /14 is, and we break it down into binary. Our 16 is 00010000. Our 17 is 00010001. Notice the 6 on the left are the common. They are all the same ones. So our summarization would be 8 bits in our first octet, 9, 10, 11, 12, 13, and our 14th bit. Our summarization is going to be, how are all of these the same? And if we do not look at the last 2 bits, they're all the same. Again, with summarization, I'm going to be doing another video on just summarization, so keep your eyes out for that. What about networks that aren't contiguous? Here is 10.108.16.0 through 31. Here's a completely different network. How do we go from this network to the other network? Our routers have to have a routing table, and they have to know the routes or the pathways to the other addresses. That's how come the router will learn the addresses, and it will forward the route based off the appropriate decision through the network. Mobile host, same thing. It will go through the internet, and that's what we'll have. So let's talk about IPv6 for a minute. And we're going to talk about the global unicast addressing format. So here we have a simple unicast address format header, our FPs, our format prefix, our top level aggregate identifier, TLA ID, we have our reserved for future use, our res, our NLA ID, next level aggregation identifier, our site level aggregator identifier, then our interface ID, and it's just going to be our interface identifier. So this is a simplified unicast address format. I don't really know why it's brought up here because we don't really talk about this, the header formatting, just yet. So how do we work on upgrading a network from IPv4 to IPv6? There's a few different ways: dual stacking, tunneling, or transitioning. You could just transition completely to IPv6, but a lot of them are doing dual stacking, and that's where IPv4 and 6 run on the same system. And the system is able to communicate in both IPv6 and 4 devices. And then just the choice of IP version is based on the name lookup of the application reference. Basically, you give them options. Tunneling is the method of encapsulating IPv6 packets for traversing an IPv4 network. Translation, this method will translate one type of the address to the other. So let's look at some guidelines to assigning names. So we're going to transition into our naming portion now. Names should be meaningful. They should not be ambiguous. They should be and case sensitive, and avoid names with unusual characters, like hyphens and underscores and asterisks, and special characters in general. Our DNS maps names to addresses and addresses to names. It supports a hierarchy naming structure, and that's how our internet works. A DNS server has a database of resources called records that map names to addresses, and that server is a zone of authority, its sphere of control. For example, when you go to google.com, it has to translate google.com. But in reality, it translates .com, and it will look through the .com zone, and then it will find Google in that reference table. Because it actually reads it backwards. It looks at the domain postfix, our .com, our .net, our .biz, our .gov. Those are looked at first, and then our domain is looked up. So our DNS normally is more of a client-server model. We will act as clients, and we will query a server that has DNS settings so that we can figure out the appropriate address of the machine or route that we're trying to get to. These can be manual or DHCP, it kind of depends. DNS resolving software may sit on the client, and it could send a query to the DNS server. Clients may ask for a recursive lookup. DNS servers may offer recursive, which allows servers to ask other servers. So just in case you have your own DNS server, if it doesn't know where an address is, where does it go? It can look at a server above itself, which is a recursive lookup, and if that server doesn't know, it will keep asking higher and higher and higher servers until it figures out the address to the name that you want. And that's DNS in a nutshell. I wanted to thank you guys, and I hope you guys have a great day. Okay, so I wanted to discuss some follow-up items. One of the first things is our APA formatting and citation. That goes for both our IPs and our discussions. Remember that we have to do all of our work according to APA manual. So if you're not sure how to do that, go online. You can type in APA formatting. If you don't want to look it up online, you can go to any of the tutorial services. We have a writing, we have a library service. They can give you additional resources on how to do APA formatting. That's important. That's not going away. In discussions, same thing. We have to be doing our citations in our discussions, because one of the big things is, for our citations, we're building off of other people's works. So it's a way for us to verify what we're claiming is supported by the literature. So when I say something at the sky is blue, you can take my word for it, or if I provide a citation, you can take an expert's word for it, and then I built off of that. So it just kind of increases your credibility. We should be at least citing in every post, or as much as possible, because again, we're trying to link what we've done back to the literature. Same thing in our IPs. Every paragraph should be tied to a source. Every paragraph is an idea, and every idea we need to have support within the literature. And I know at this level it's not that big of an issue, but you want to get in the habit of doing that, so when you start doing higher level work, it's second nature. Also, length. We don't need posts that are great job. I mean, don't get me wrong, it does add to it, but when I start grading for posts, I'm not doing full credit for those that have 3 posts and 2 of them are great jobs. I don't count the great jobs as a post. For our discussion board, I'm looking for 3 solid responses with citations. For our papers, I'm looking for 3 pages of content with citations. So what I mean by content is, that's 3 papers on topic. That's not a cover page, that's not your reference page, that's 3 content pages. 2 if you're really good, but I'm really looking for 3 if you're doing diagrams. Diagrams totally are okay, as long as you're doing them within APA formatting. Lastly, grading. Again, I grade heavily off of attempt, like if you're putting an effort into it. Like if you did 2 pages and you did a few citations, and I could see that you were making an effort, I'll meet you. But if you post once, or you did a page and a half with 1 citation, you know, that really isn't you making an effort. If you get stuck, don't get me wrong, some people a page is a lot. If you get stuck, you have plenty of resources to bolster up your paper. You can contact me, I'll help you. If you don't want to contact me, we have a writing center, we have a tutorial center, we have plenty of help for you to get. If you need tutoring, there's a lot of tutoring out there. And again, provided from the school. All you have to do is say something. For our tutorial lab, we have tutorial services for SQL, we have tutorial services for database, we have tutorial services for math, English, writing, research, library services. I mean, we have a great amount of tutorial services. And if we don't offer tutoring in a specific area, you can ask for it specifically, and they will find tutors for you. So you could not get tutoring, because you can. If you ask for help, the school will get it. If you cannot get it from the school, there's other help. I will sit down with you. I will do as much as I can with you if you need one-on-one. If you need tutoring and you don't get tutoring, that's not a failure on my part. That's not a failure on the school's part. That's only a failure on your part, because there's plenty of opportunities there. You have my number, you have my email, you have 2 emails from me, you have my cell phone number, you have plenty of ways to get a hold of me if you need help. And again, if you don't capitalize on help and you need help, that's on you. Because there's plenty of help out there. All you have to do is say something. Thank you.